Let's start at the surface and work down towards the bottom. At the top of the lake, this is getting the infrared radiation, the sunlight penetrating. This receives the heat. During summertime and stratification, it is not uncommon for temperatures to range anywhere from about 20 to 25 degrees centigrade. As you go further below the surface, obviously it gets cooler, but since the temperature differences aren't that great, the differences in density aren't that great. So that wind action, like we have today with waves, can cause mixing within that epilimnion. So the temperatures in this upper layer stay pretty much the same, like I said, somewhere between 20 and 25. But now you've gotten to the point, maybe 10, 15 meters down, depending on the depth of light penetration. Now the Ashokan Reservoir is very clear in terms of the water, very little turbidity, very little color, so that light penetrates quite deeply. It may set up about 15 meters. All of a sudden, your heat source has been cut off because your infrared is no longer penetrating. So that now the temperature changes very, very drastically. This is a zone called the thermocline. It goes by a number of different names, but thermocline is probably most widely accepted. In the thermocline, because you've now lost your heat, your infrareds, the temperature drops at least 1 degrees Celsius per meter. Actually, the drop is usually faster than that. Now, if you've ever done any diving in a lake, especially one that's very turbid so that this thermocline is up higher, that is, the heat's filtered out faster, thermocline therefore is shallower, you know what hitting the thermocline is like, because you're diving through relatively warm water, 20 to 25 degrees Celsius, excuse me, and all of a sudden you start diving down into this zone, this layer where the water gets very cold very fast. That's the thermocline. Temperatures can drop anywhere from about 20 degrees centigrade down to as low as 6 degrees centigrade within a matter of 10 or 15 meters. Now that's a tremendous change in temperature, but this is important. That's also a major change in density. So that in that short zone of water, density changes are so rapid that this layer will not mix. In other words, it sets up a block, an isolation between the upper strata, the epilimnion we've already discussed, and the lower strata below that thermocline, which is called the hypolimnium, which we'll discuss in a moment. So we have this barrier. Now biologically, this is very important during summer stratification, because as I want to emphasize, remember, that lower zone, that third strata that's at the bottom, known as the hypolimnion, that is isolated during summer from the rest of the lake. No mixing occurs within that zone. Now, how big is the hypolimnion? Depends on the depth of the lake. In an extremely deep lake, like the Ashokan Reservoir or the Finger Lakes or some of the Great Lakes, the hypolimnion can be huge, can be hundreds of feet deep. Whatever the depth, the temperature within this cold water zone stays about the same year-round. Remember, water's densest at 4 degrees Celsius. That's the heavy water. That's on the bottom. In fact, that whole hypolimnion, that whole lower layer, usually ranges from about 4 degrees to 6, 7, 8, that's about as high as it gets, degrees Celsius within that hypolimnion. The ironic part is, the density differences are very minimal. And that water would be easy to mix were there a force to mix it. But because of the thermocline above it, that rapid density layer that can't mix, it seals off the hypolimnion. Excuse me. So that hypolimnetic area remains unmixed. It can mix internally by a process or by a physical phenomenon known as seiches, but I don't want to get into a discussion of seiches. But it can mix internally, but not with the other layers. So it remains isolated all during summer stratification. What does this mean to a lake in terms of life of the lake? Well, in some lakes, that's no problem. In an oligotrophic type lake, and by the way, we've already discussed the trophic statuses of lakes. In an oligotrophic lake, such as the Ashokan Reservoir, basically what this means is that during summer stratification, since there's so little organic matter on the bottom, the high level of oxygen in that hypolimnion, and remember, because it's colder, it holds more oxygen, that high level of oxygen is maintained throughout the summer. Now, this is ideal for cold water species. This particular habitat behind us has excellent populations of different types of trout that remain in that hypolimnion during the summer. There's plenty of oxygen, they're not limited, they stay in the cold water, food is available, that's fine. But in that eutrophic lake we've discussed, remember that because it is very rich and there's a tremendous amount of production at the surface, remember all of the plankton growth, phytoplankton, zooplankton, etc. Since there is so much production, a tremendous amount of organic matter is deposited on the bottom. And this organic matter during the summertime undergoes decomposition. Well, obviously, what's going to happen is that in a lake such as this, where there's a tremendous amount of decomposition on the bottom, that oxygen budget that we started with at the beginning of the summer is going to be slowly eroded. How fast does the oxygen disappear? Well, basically it depends on how fast decomposition occurs. The heavier the organic loading, the faster the decomposition, the greater the use of oxygen. In a hyper-eutrophic lake, that is a very, very rich one with a tremendous amount of organic loading on the bottom, oxygen may disappear by the middle of June. In other types of lakes where the loading is not that heavy, it may maintain oxygen till July or even August. But the main point is this, remember, once that oxygen is gone, once it's disappeared, then only species that are anaerobic can survive at these depths in this zone with no oxygen. In fact, and we're only talking about a few types of species. Some of the anaerobic bacteria, a few types of invertebrates that can survive in little or no oxygen. But in terms of fish, they can't survive there. In a lot of states, biologists have stocked fish in lakes, salmon and trout, in eutrophic type of lakes where oxygen becomes depleted on the bottom. These salmon and trout have no place to live during the summer. They can live on the bottom in the hypolimnion because there's no oxygen. They can live on the top where there is oxygen because the water's too warm in the epilimnion. So basically what they're forced into is this little shallow, relatively narrow band or strata called the thermocline. Well, the problem with the thermocline is it does not have the food available that either the epilimnion or the hypolimnion would have in a normal oligotrophic trout salmon type lake. So in habitats such as this, usually the trout that are trapped in the thermocline simply starve to death. It is not a good habitat for trout.